Hello. So on this video, we're going to take a standard Runge-Kutta solver for solving an ordinary differential equation and convert it into a solver for a partial differential equation. So here I have a Runge-Kutta solver. I've got a function using this sort of symbolic thing. So this saying that the variables are t and then y, and they're arranged in this way. I've written this just as a one-dimensional solver here. So the f is going to be used down here in 4 spots along our Runge-Kutta evaluation. Here's our normal Runge-Kutta update formula, and we're going to plot it. So we're running from time 0 to time 5. And it looks something like this. My initial condition is the number 1, and I'm taking 100 grid points along the way. Great. So this is nice. Our Runge-Kutta seems to be working okay. Of course, we should test this and verify that the error is a -4. But let's suppose that we've already done that. We want to take this whole thing and convert it into something which can now solve a partial differential equation. So the first thing I'm going to do is sort of just copy paste some stuff from a previous video where we looked at taking derivatives using Fourier transforms. So we've got here, this is our domain size. This is the number of grid points for the spatial resolution. This is our step size. And here's our x. I've also written a little reminder here in case you ever forget what the step size should be, that it should be L divided by n-1 or n plus 1. Just think about it with a small example like 4 points from 0 to 1. For the Fourier, if we're thinking about things being periodic, the 1 and the 0 count as the same point, so we don't want to include the last one. And so we should have 4 evenly spaced grid points along there, sort of kind of including 1 as a kind of periodically. In our minds, 1 is there, but computationally it's not. So we would just have them evenly spaced like this, and so our dx would need to be 1/4. That is the length of the domain divided by n. Okay, so in addition to that, we have a spatial grid point. There's some spatial grid points, and we've got this ik vector, which is I times the places where these locations are stored. We also need, and I just want to emphasize this again, for let's say for the for first derivative, or really for odd order derivatives, it would be something like this. For this one would be for second derivative. I guess I don't need a dash here. And for the second derivative, of course, we're going to square this. Oops, excuse me. We're going to square I, which is just gives us a -1. And we'll square this bit too. And let's give this a new name. Maybe we'll call it k squared, KSQ. All right, great. Now notice we have a little bit of a problem because we have n grid points here in time and also n grid points in space. So I just wanted to highlight this because sometimes it can be a point of confusion. Obviously, Matlab is not going to like it if we use the same variable for 2 different things. So we'll get all kinds of errors. So I sometimes call this something like number of times or number of time steps. If you want a little longer name for it, something like that. Maybe I'll just call it n times here. And let's maybe take maybe 100 or 1,000 times. It doesn't really matter. Something like that. All right, we've got all of this factored in. But we should say what we're doing. So up here, we want to solve the heat equation. Using Fourier methods in space and Runge-Kutta for in time. The equation takes form. So it's nice sometimes to report up here, your heat equation might look a little different than somebody else's. So maybe something like new times u xx. It kind of shows that we're using, for instance, this new as the variable, that kind of thing. As the excuse me, as the viscosity. Somebody else might use a different letter. Okay, so we're off to a decent start importing some of our previous code and kind of smashing these together a little bit. Now, we need to modify a few other things. First of all, this time information, I'm going to cut that and paste it up here. So sort of all the time stuff is happening in one place. Now, we also have our solution, and our initial data is this y0. Of course, for the heat equation, our initial data is not just a number, but it's an entire function, right? So we'll need to change that. So let's just delete the y0 for now. The f, let's see, I better be careful here. So here we'll divide the dt by number of times minus 1, okay. The f in this case, we'll actually change this a little bit. So rather than passing f as a symbolic function, within the function, that is the right-hand side of the function, if you think about what we'll do is we'll take the Fourier transform in space, not in time, of this function. So that'll leave us with some time derivatives on the left, and on the right we'll have, well, negative k squared times the Fourier coefficients of u times this factor nu. So each time we'll want to multiply by this whole vector. And you can do that in a Fourier transform like this, but later we're going to want to look at more complicated equations, nonlinear equations, and we might be doing some very involved things on the right-hand side. So rather than taking f as a symbolic function where we just sort of pass this thing in, let's delete that and actually set this as a new function. So to do that, I'm going to make the whole thing a function. So let's say this is function heat equation. Maybe we'll do heat 1D. And I won't put any arguments or any output for that. And I'll just end it here and save this as heat 1D. Heat 1. Great. Okay. So we want to solve this equation. All right, so now down here in our Runge-Kutta, we'll need a new function. We can leave it as the name f, and to do that, we would do something like, let's see, function. So we start another function. Sometimes it's good to remind ourselves that this is end function heat 1D. We're starting another function here, and let's call this this function. So we can stick with the name f here, but for some reason, I think it's a little nicer to remember this is just the right-hand side of the PDE. So I like to call mine RHS for right-hand side, but you could call it F or whatever you like. And it brings in T and then some other variable. We'll maybe come back to that in a minute. I'll just call it Y for the moment. All right, so this will do if we had something like, let's just call the output Z, just to give it a name. If we said Z is equal to negative T times Y squared, we will get the same functionality that we had from our previous Runge-Kutta code. So this is how we could code that without the handy @ sign if we wanted to do it a slightly different way. Here, of course, we just say end function RHS. These comments are just for our own reminders. We don't really need to do that, but sometimes it makes it a little more clear. And you can even do something like put some dashes or equal signs here to visually make your code a little bit easier to see. Okay, great. But we want to do something more complicated in this position. So we have our spatial information. Maybe we'll kind of compress that so we can see what's going on there in space. We've got our time information here. And now we want to deal with our initial condition. So to do that, let's just take an initial condition to get started with. First of all, for PDEs, it's more common to call the solution U instead of Y. I guess for unknown, something like that. So I'll write U is just sine of x, and maybe let's make it a little more interesting, plus maybe cosine of 7 times x. Maybe 7x times 0.1. So it should be a sine wave with a small oscillation, higher frequency oscillation on it. Okay, great. Then we'll need to, so the first thing we'll need to do, the idea is that we'll we'll evolve this equation in Fourier space. So that is in Fourier space, this is, say, u hat at k, and really we want the time derivative of that. It's going to be a little awkward to write up here. d over dt of u hat k, if you want to see it that way, is equal to minus nu times k squared times u hat k. Okay, it's a little awkward writing this just in a single line like that. LaTeX would make this a little nicer, but this is roughly the idea. Now we might be saying, hey, wait a minute, can't we solve this directly just using an integrating factor? And the answer is yes. It's just that when we want to adapt this to nonlinear problems and that kind of thing, we won't have such a nice way to solve for the Fourier coefficients explicitly. So we just want to solve them. We'll just kind of take a nice generic that is explicit approach to this. Okay, so now we want to just use our Runge-Kutta solver on this system of ODEs. Okay, great. So what we'll do is compute u hat to be the FFT of u, like we did in a previous video. And the variable that we're going to be evolving here is that u hat. So with the Runge-Kutta code, we were saving it each time the solution, and therefore we were able to plot it and that kind of thing. You can certainly do that for a one-dimensional PDE. It's not a huge amount of data, but for a two-dimensional or three-dimensional PDE, it starts to become quite a bit of data, sometimes gigabytes or terabytes of information that you're needing to save if you really want to save every single time step. So instead of doing that, let's just pass in u hat. So not u hat at previous, this will be u hat at the previous time, but we won't be saving it as we go. And that means we won't need these advancement steps either. So I'll call this, so this will just be u hat, and it will be, so we'll have the old u hat here, and it will overwrite itself with this update. So each time through the loop, we will be forgetting what u hat was previously, and we'll just be using it once to, well, I guess at each stage to update the new u hat. We can do something similar here for the time, but time is just a single vector, and it's fine to leave it like this. Oh, I keep making little mistakes. This should be n times there. Okay, great. So here's our updated Runge-Kutta algorithm itself. Now we need to update the right-hand side. And I like to write the input variable as the same name as what I'm plugging in here. So we've got a u hat coming in, and we just want to compute what is going out. So for that, we need to multiply by I times k, right? This ik vector here, or sorry, excuse me, it's really the k squared vector. And we also need to multiply by nu. But notice that this function down here will only know the inputs coming in. So we have to send those inputs down to the function. So one way we do that would be something like, let's input k squared here and nu. And we'd have to do that on each instance of the function. This is not the only way to do it. There are many ways to do it, but this is maybe a quick way to see what's going on there. Okay, so we'll just put in this k squared at each point in the function and the nu. Okay, great. That means we also have to do it down here. So k squared nu. Okay, now we have our same number of arguments at the top and the bottom. It's highlighting these because Matlab is saying, hey, you're inputting u hat and k squared and nu, but you're not really using them down here. So let's use them. So we could say something like, excuse me, u hat is, it needs to get multiplied by u. So I guess if we want, we could call our output z. So it's just excuse me, it's k squared. Whoops, k squared times nu hat. Times u hat times nu. But don't forget, this vector, these two objects are vectors, so we should really have a dot times there. We don't need one here because nu is just a scalar number. And it seems all right there. Of course, we forgot to put in what nu is, and I like to put that in toward the top of the program because it can be somewhat useful to see what this value of nu is, to be able to just code it quickly at the top of the program. Now, we've written ik here. Technically, we don't need the ik for the heat equation. If we had some kind of drift heat equation or transport diffusion equation, something like this, then maybe we would use the ik, but for now we don't need it. So we could delete it, but maybe we'll need it later, so we'll just comment it out for now. When we're all done with that, so each time through, we're calling this function. And again, the reason, I mean, we could just kind of hard code this up here, but I like to keep the time stepper separate from what is happening on the right-hand side. This allows you to swap in and out different time steppers to change to the right-hand side as you see fit. But also, we're in the future going to be doing things that are significantly more complicated than just multiplying a few things together down here. Okay, so each time through the loop, this is happening, but we might want to see the result. So in order to do that, we should plot the result. If we do something like just plot u hat, of course, this is in Fourier space, so that's not exactly what we want to see. What we need to do is take an inverse Fourier transform of that function. Remembering that the symmetric tag is appropriate when we're using functions which are real valued. U starts out as real valued and should remain real valued. So this just speeds it up a little bit. Let's take a look at how this looks and see if we come across any errors. I'm not saying it's perfect. Sometimes I like to just run things and see how they go. So if we run it, we get an error. Oh, well, okay, that's a typo. So line 30, FTT, FFT. All right, so we have something like this. And notice that there's no animation here. Something's looking a little bit wobbly. What's going on? Well, what happens is that each time through the loop, it sort of takes MATLAB a little bit of time to send all this information off to be rastered to draw the graphics. Yeah, so what we can do is we can type draw now, and that will force MATLAB to draw the picture at each moment. And we see just a little bit of movement in the heat equation there. Let's run out to a larger time, so maybe time 50. Let's also increase our spatial resolution a little bit. So maybe this could be 2 to the 8th, something like this. And that might be a little too small of a time step for this. Let's take a look. I think it's definitely going to be too small. Oh, index exceeds number of array elements there. Must not exceed 100. Why is that happening? I need n times there again. Whoops. All right. So we're seeing it. Let's type close all. There we go. So we see this really oscillatory, crazy looking thing. And that has to do with the fact that our time step, so if you saw that was like 10 to the 200 or something. That happens when your time step is not small enough for this type of explicit method. So it turns out to be a little bit nicer to, instead of setting the time step up here, we'll set it a little bit lower. And I'll do it a slightly different way. So rather than setting up the number of times in advance, I'll wait to until we've calculated this dx. And down here, we'll calculate the dt based off the dx. So we'll see this a little bit later, but we need a constant number, which turns out 2 divided by pi squared is pretty good. But we'll use something smaller than that. 0.2 is smaller than 2 divided by pi squared. And then we'll multiply that by dx squared divided by nu. So this is called the Courant-Friedrichs-Lewy condition. And this has to do with stability. So if you use an implicit method, then the CFL condition is not as much of an issue. After that, we should redefine these other bits. Whoops. So we can define time to be, let's say, we go from, say, t0 out to, in steps of size dt, out to final time, and our end times can be the length of that time. And then we'll run n times -1 because we've already computed the first one. Okay, great. So this should give us something that, there we go, something that looks quite a bit more stable. It's a little bit more dramatic. Oh, notice the redrawing of the axes there. So if we fix the axes by doing something like axis, or maybe we just want to fix the up and down bits. So if we do something like y lim will be, say, maybe for now we'll just do something like -1 up to 1, maybe -2 up to 2. All right, let's make this maybe a little bit easier to see. We'll do line width 2, and then let's increase this just to make it a little bit more dramatic. Cosine of 33x. So there we see this nice kind of shrinking down size. I guess we should really plot this versus x, and maybe we should say something like x lim is, say, 0 out to pi. I guess we could have done that in a single command with axis, but there we go. So we get a pretty nice plot of the heat equation. Hey, look at that. We just solved a PDE. So that's a good place to stop.